area is given by A. So area can be written as L square because we have considered the side as L, then area will be L square and L cube be the volume. Molecule moving along x-axis will hit one of the plane with velocity Vx. Kinetic energy of a gas molecule is directly proportional to absolute temperature. As the temperature increases, the energy gained by the molecule will be more and the kinetic energy also increases. Hello everyone, welcome to session 2 of chapter 13, Kinetic Theory of Gases. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in the previous session, we had a discussion about the brief introduction about kinetic theory of gases and also various terms involved in understanding the kinetic theory of gases. We have also studied about the postulates of kinetic theory and many more topics. So in today's session, we are going to learn some more concepts regarding the kinetic theory of gases. Let us begin with the expression for pressure of an ideal gas. So for example, if you confine an ideal gas, if you take an ideal gas and confine in a cylinder or in a cubical vessel, what is the pressure exerted by the ideal gas? We are going to find the expression for it. For that, I have considered a cubical vessel. So let us now derive this. Consider a gas enclosed in a cube of side L. So let us consider the side of the cube be L. If the side is L, area is given by A. So area can be written as L square because we have considered the side as L, then area will be L square and L cube be the volume. So here I have considered a cube of length or the side L, then the area is given by L square and the volume of the gas inside the vessel is given by L cube. Let us consider N be the number of molecules per unit volume of the gas. Here we have considered an ideal gas which is enclosed in a cubical vessel. So N be the number of molecules per unit volume of the gas and M be the mass of each molecule. We have N number of molecules, let M be the mass of each molecule. Now observe this picture carefully. So let us consider O. This is be the origin of three-dimensional or three-coordinate system. O be the origin of three-dimensional coordinate system. So here the gas is enclosed in this cubical vessel. Now according to the postulates of kinetic theory, we know that the gas molecules will move random in direction and during this motion they will collide with the neighboring molecules. They also hit the walls of the container. This is the general concept we know about it. And now applying the same knowledge here in deriving the pressure. So let us say that a molecule called A of the gas moving with the velocity V. Then it is moving with velocity V, but it can move in any direction. We know that the gas molecule is not bounded, not restricted to move only in particular direction. It can randomly move along x-axis, y-axis as well as z-axis. So A be the gas molecule which is moving with the velocity V, then Vx, Vy, Vz are the components of V along x, y and z directions respectively. So if the gas molecule is moving along x-axis, then we can say that it is moving with velocity Vx. If it is moving along y, then we can say that it's moving with velocity Vy. Similarly for z-axis, that is Vz. So the molecule moving along x-axis will hit one of the plane with velocity Vx. Now you can observe this coordinate system or the cubical vessel. So let us say that the gas molecule is moving along x direction and it will hit this wall. It is moving with velocity Vx. This is our consideration for deriving the expression for pressure. Now we know that as the gas molecule go and hit the wall, it will rebound back because it has elastic property. So as the collision is elastic, therefore it rebounds with the same velocity. The gas molecule is moving and hitting the wall and it rebounds with the same velocity but in the opposite direction. So what is the total momentum transferred to the wall? So momentum before the collision will be equal to momentum after the collision because it moves with same velocity before it hits the wall, after it hits the wall and rebounds. So momentum before collision is equal to momentum after collision. So how to find the change in momentum? Change in momentum is nothing but the final momentum minus initial momentum. What is final momentum? It is minus Vx. Minus Vx and initial momentum is Vx because we have considered this wall where the molecule is moving along x direction with velocity vx, because it is elastic collision, the molecule will hit the wall and it rebounds back with opposite direction, that is minus vx. So it is minus vx minus mvx, because momentum is nothing but p is equal to mv. It has some mass, it has got also some velocity. So minus mvx minus mvx is the initial momentum. So we will get minus 2 mvx is the change in momentum. So the momentum transferred to the wall in each collision is equal to 2 mvx. What is the number of molecules that is enclosed in the cubical vessel? So the number of molecules hitting the wall in small interval of time, that is delta t, is equal to half into total number of molecules in a given volume. Why it is half? Because we know that in random motion, or when number of molecules are going and hitting the wall, so during that time half of the molecules will be rebounding back, so at the same time. So in the time interval delta t, half of the total number of molecule will go and collide with the walls of the container. So it will be half into total number of molecule in the given volume is n, that is number of molecule in the given area which is moving with velocity vx at a particular time interval, that is delta t, because this is nothing but volume. Volume is given by area into distance traveled. So distance is nothing but speed into time. So these many numbers of molecule hits the wall in a small interval of time, that is delta t. So the total momentum transferred to the wall in time delta t is given by 2 mvx into half into navx into delta t. Since we are writing the expression for momentum now, it is denoted by delta p. So now solving this, 2 and 2 will be cancelled. Vx we have here, vx we have here. So we remain with n m, vx into vx is vx square delta t into a. So I'll take it as equation 1. So we know that the molecule is moving with certain velocity and it has got some mass. So we can make use of Newton's second law of motion. From Newton's second law of motion, how Newton's second law of motion is related with the momentum, that is rate of change of momentum. F is equal to delta p divided by delta t. But what is delta p? We have got the expression here, that is nmvx square delta t into a divided by delta t. We can cancel these two and we remain with nmvx square into a. So this will be our equation 2. Now what is the total pressure on a particular wall? One side wall we have considered, on which the gas molecule is going and hitting and rebounding back. So we are considering that scenario. What is the total pressure on the wall? That is P is equal to force divided by area. But what is force? We have got the expression here, that is nmvx square A divided by A. A and A will be cancelled and we remain with Px is equal to nmvx square. What is Vx? It is velocity of the molecule in x direction. So I'll take it as equation 3. Now, if we have considered only one scenario, that is a molecule is going and hitting one particular wall, but we know that the gas molecules will be in random motion. We have considered the 3-dimensional coordinate system, which means the molecule can move with velocity along x direction, y direction as well as z direction. So, but we have got the expression only for x direction. Similarly, we can write the expression for y, that is pressure exerted by a molecule along y axis on a wall. It is Py is equal to nmvy square, and similarly Pz is equal to nmvz square along z direction. So as gas molecules have same properties in all direction, we can say that Px is equal to Py is equal to Pz, that is P. P means the pressure exerted by the gas. So now we can write the average pressure exerted by a gas molecule as P is equal to, here P is nothing but the total pressure exerted by a gas molecule, which is equal to Px plus Py plus Cpz divided by 3, and that can be written as 1 by 3 into Px plus Py plus Pz. Now what is Px? We have derived here, it is nmvx square. So let us substitute all the terms for Px, Py and Pz respectively. We get P is equal to 1 by 3 into nmvx square plus nmvy square plus nmvz square. from the previous equations. So now here we can see that Nm is common in all the terms. So take this outside. I can write it as P is equal to Nm divided by 3 into Vy square plus Vz square are the remaining terms inside the brackets. Now it is nothing but the velocity of molecule along x, y and z direction. So we can replace these Vx, Vy, Vz with V. That gives us the velocity. Root means square velocity of a molecule. Now we can write it as P is equal to Nm divided by 3 into V square. So here in this equation, P is nothing but the pressure exerted by the gas, N is the number of molecules per unit volume, M is the mass of each molecule, and V square is the root means square velocity of the molecules. So here we can observe equation 6 also represents the pressure exerted by a gas molecule, that is P is equal to Nm by 3 into V square, and equation 7 is also nothing but the pressure exerted by the gas molecule. So both the equation 6 and equation 7 are expression for pressure exerted by gas molecules. Expression for average kinetic energy of molecule in terms of absolute temperature. So far we have derived an expression for pressure exerted by a gas molecule. Let us now write the expression for average kinetic energy of a gas molecule in terms of absolute temperature. And the kinetic energy is given by half mv square. How it is related with absolute temperature? That is given by the expression 3 by 2 kb into T, where in this expression m is the mass of each molecule, kb is nothing but the Boltzmann constant. It is given by R divided by Na, where R is the universal gas constant and Na is the Avogadro number, and the value is given by 1.38 into 10 power minus 3 joule per Kelvin. Now here in this expression you can observe T is nothing but the absolute temperature. We are writing expression which relates the average kinetic energy of gas molecule in terms of absolute temperature. This is the average kinetic energy of a gas molecule in terms of temperature, absolute temperature. It can be given by 3 by 2 kb into T according to law of equipartition of energy. Here we know that the kinetic energy of a gas molecule is directly proportional to absolute temperature. As the temperature increases, the energy gained by the molecule will be more and the kinetic energy also increases. Say for example, according to kinetic theory of gases, when the temperature is 0 Kelvin, then the kinetic energy of the gas molecule is 0, because we know that the gas molecule's kinetic energy is directly proportional to its temperature, absolute temperature. So no molecule can have kinetic energy less than 0, because no temperature can be lower than 273.15 degree Celsius. So here from this we can say that the kinetic energy of a gas molecule is absolutely directly proportional to temperature. As the temperature increases, kinetic energy of a gas molecule will increase. As the temperature decreases, the energy gained by a gas molecule will decrease. So these are few important expressions from the chapter Kinetic Theory of Gases. In the next session, we will learn some more concepts. Until then, please take care all of you. See you all in the next session. Keep learning. Thank you.